Hi there, Joshua here. I went to the supermarket this week and I said to the bloke working there, you've got some nice chickens, but I'm looking for one that weighs about 3.14 kilograms. He said, 3.14 kilograms, that's a bit specific. What are you making? I said, chicken pie. Let's get on with the lesson. Right, so welcome to this lesson on transforming graphs. So what I'm going to do in this lesson is I'm going to draw lots of different graphs. So the first graph I'm going to draw is y equals the square root of x. I know that's a graph some of you might not have seen before, so I'll draw that. And then what I'll do is I'll change the equation slightly. I'll change the expression on this side in a few different ways. And we'll see how it affects the position of the graph. We'll see how the graph moves. So I'll draw the graph first though. I'll draw this graph by doing a table of values. And I'll just choose some x values that are easy to square root. So I'll choose 0, 1, 4 and 9, because they're quite easy to square root. So let's work out y for these x values. So when x is 0, y is just the square root of 0, which is 0. When x is 1, y is the square root of 1, which is 1. When x is 4, the square root of 4 is 2, because 2 times 2 is 4. And when x is 9, the square root of 9 is 3. So we've got 4 points there. Let's plot them on the grid and see what the graph looks like. So 0, 0 just goes over here. 1, 1 is just over here. 4, 2 is right 4 up 2, just over here. And 9, 3 is right 9 up 3. So right 9 up 3, just over here. So you can see the graph sort of curves around and it gets less steep as you go further to the right. It never flattens out completely, it does keep increasing. It does sort of curve around like that. Right, so what I'll do now is I'll draw 2 more copies of the same graph. Right, so I've just made 2 more copies of the same graph. There they are. So I've got 3 graphs of y equals the square root of x altogether. Now what I'm going to do is I'm going to take the original equation, y equals the square root of x, and what I'm going to do is I'm going to stick a plus 2 on the end of this expression. I'm going to stick a plus 2 on the end. So what's that graph going to look like? How's it going to compare with the original graph? Well, some of you might know this already, but I'll do a table of values. I'll do a table of values anyway, just to help. I'll use the same x values, 0, 1, 4 and 9, because they're easy to square root. So when x is 0, y is just the square root of 0 plus 2. Well, the square root of 0 is still 0, plus 2 is 2. So when x is 1, y is just the square root of 1, which is 1, plus 2, which is 3. So notice the y values are basically 2 bigger than before, because you're adding 2 at the end, aren't you? So you're still square rooting the x values, but you're just adding 2 after that. So when you put 4 in, the square root of 4 is 2, just like it was before. Then you're adding 2, 2 plus 2 is 4. When you put 9 in, the square root of 9 is 3, and then you're adding 2, so you get 5. So all the y values are 2 bigger than they were before. So that means on the graph, these points are 2 higher than the original points, because the y coordinates are 2 bigger. So 0, 2 is over here, which is 2 higher than that point. 1, 3 is up here, 2 higher than that point. 4, 4 is right 4 up 4, over there, 2 higher than that point. And 9, 5 is right 9 up 5, up here, 2 higher than that point. So if I draw the graph, it's just the original graph moved up 2 places. So we say the graph has been translated up. A translation is just a movement in a straight line. So where the graph has been translated 2 places up, basically. And that's what sticking a plus 2 on the end does. So if you add something to the whole expression, it just moves the graph up, basically. Now what would I have to do to the expression, to the original expression, for the graph to move down to? What do you think I'd have to do there? That's right. I'd have to replace. I'd have to stick a minus 2 on the end. So if I draw a graph of y equals the square root of x, take away 2. Surely that's going to make the graph move, the original graph move down to. Yeah, I mean, let's do a quick table of values. I think we know what's going to happen. Same x values again. So we're still square rooting all the x values, but this time we're taking away 2 after that. So all the y values are going to be 2 smaller than they were here. So instead of a y value of 0, we're going to get minus 2. Instead of a y value of 1, we're going to get minus 1. Instead of a y value of 2, we're going to get 0. Instead of a y value of 3, we're going to get a y value of 1. So all the y values are going to be 2 smaller because we're taking away 2. So the points are actually going to be 2 lower than they were originally. Just over here, that's 1 minus 1's over there. 4, 0 is just over here. And 9, 1 is right 9 up 1, just over there. So if I join these points up, it's just the original graph sort of moved down 2 places. It's the original graph translated, it's the original graph translated down 2 places. Right, what if I take the original equation, y equals the square root of x, and this time instead of adding or subtracting something to this side, what if I double the whole side? So what if I multiply the whole side by 2 and draw a graph of y equals 2 times the square root of x? What's that going to look like, I wonder? Well, again, some of you might know this already, but I'll do a table of values to help out. Let's see what happens. I'll use the same x values as before, 0, 1, 4 and 9. Now, is it fair to say that the the y values are going to be kind of the same as they were before, but they're going to be doubled, basically? Because we're still square rooting x, but then we're doubling after that. So when x is 0, the square root of 0 is 0, but then you're doubling it, so you get 0. So that doesn't show it very well because it doesn't change. Let's try 1. So the square root of 1 is 1, just like it was before, and then you're doubling it, so which is 2. When you put 4 in, the square root of 4 is 2, but then you're doubling it, so you get 4. And when you put 9 in, the square root of 9 is 3, and then 2 times 3 is 6. So notice all the y values are just double what they were originally. So on the grid, but that basically just means that all the points are going to be 2 times higher than they were originally. So 0, 0 is still over here. But 1, 2 is right 1 up 2. 4, 4 is right 4 up 4. So just over here, sort of twice as high as that point. And 9, 6 is right 9 up 6 up here, twice as high as that point. And when I say twice as high, I basically mean that the distance sort of to the point from the x-axis is double what it was before. So this distance here is double the original distance, basically. And that's true for every pair of points sort of in line. So if I draw the graph, it's the original graph, but it looks like it's been stretched. It's the original graph stretched upwards. We say stretched upwards by a scale factor of 2 because all the points are twice as high as they were originally. That's what doubling the whole expression does. Now, what would I have to do to, instead of stretch the graph up by a factor of 2, to squash it down by a factor of 2? What would I have to do to this expression so all the points were squashed down 2 times closer to the x-axis, do you think? Correct. I'd have to divide the expression by 2. So I'd have to take this equation, y equals the square root of x, and instead of multiplying by 2, I'd have to divide it by 2. Or multiply it by half, the same thing. So if I stuck a half at the front, which is kind of like, which is basically dividing it by 2, that's surely going to cause a squash. Let's do a quick table of values though. 0, 1, 4 and 9. So yeah, we're still square rooting the x values, but we're halving them. We're halving after that. So all the y values are just going to be half of what they were before. Half of 0 is still 0. Half of 1 is 0.5. Half of 2 is 4. Half is 4. Sorry, is 1. Half of 3 is 1.5. So these are going to be the new y values, half of what they were originally. So on the graph, all the points are just going to be half as high as the original points. So 0, 0 is still going to be over there. But 1, 0.5 is going to be over here, half as high as that point. 4, 1 is just over here, half as high as that point. 9, 1.5, just over here, half as high as that point. So this distance here to this point is half of the original distance to that point, sort of from the x-axis. So if I join these points up, it's the original graph, but it's squashed. It's squashed by a factor of 2 in the sense that all the points are 2 times closer to the x-axis. So that's what that graph looks like. And let's just do one more down here. So I'll take the original equation, y equals the square root of x. There we go. And I'll stick a minus sign in front of it. I'll stick a minus sign in front of the whole expression. What effect is that going to have, I wonder? Well, again, some of you might know this already. But again, I'll do a table of values one more time, just to help out. 0, 1, 4 and 9. I'll use the same x values as before. Now y is minus root x, so when you put 0 in, the square root of 0 is 0, and then minus 0 is actually still 0. That doesn't change. When you put 1 in, the square root of 1 is 1, just like before, but then you're making it negative, so y is minus 1. The square root of 4 is 2, so y is minus 2. So the y values are just the negative of what they were before, basically. So when x is 9, the square root of 9 is 3, then y is minus 3. So each y value is sort of like the negative of what it was before. So each point is going to sort of be reflected down. So if I plot these points, 0, 0 is still there. But 1 minus 1 is right 1 down 1. So it's sort of that point reflected down. 4 minus 2 is right 4 down 2. So it's sort of that point reflected down. And 9 minus 3 is right 9 down 3, so it's that point reflected down. So the graph is just it's the original graph reflected in the x-axis. It's sort of like the original graph reflected down. Any point up here gets reflected down, and if there had been any points down here, they would have been reflected up. So that's what sticking a minus sign does. It makes all the positive y values negative, and any negative y values positive. So it reflects the graph in the x-axis. Now, if you notice, all these transformations have something in common. They're all vertical transformations. Each point, all the points have moved up or down in some way. So over here, for this graph, all the points moved up 2 places. For this graph, all the points moved down 2 places. For these graphs, the points were either stretched up or squashed down. For this graph over here, the points were all reflected down. You might be wondering what you need to do to the expression to get the graph to move horizontally, to get the graph to move left or right, and that's what I'm going to do next. Right, let's do some horizontal transformations now. So you might be wondering, how do you change the equation to get the graph to move horizontally? Well, what you do is you just take the original equation and you just replace the x with something else. So what I'm going to do is I'm going to take the original equation, y equals the square root of x, and I'm going to replace the x with x minus 2. So I'm going to replace the x with x minus 2. So how do you think the graph is going to move? These are difficult to predict, so if you haven't seen it before, it's very, very difficult to predict where it's going to end up. So I'll do a table of values, x and y. And to understand the effect of replacing x with x minus 2, I'm going to keep the y values the same, actually. I'm going to choose the same y values that I had before. And I'm going to think to myself, what x values do I need to get the same y values that I had before? So, for example, to get a y value of 0, what x value do I need in here? Well, the square root of 0 is 0, so I want x minus 2 to be 0. Well, if x minus 2 is 0, what's x? Well, x has to be 2. Because 2 take away 2 is 0. And then when you square root that, you get 0. We'll do another one because that was a bit complicated. So to get a y value of 1, what x value do we need here? Well, the square root of 1 is 1. So we want x minus 2 to be 1. We want what's in here to be 1. If x minus 2 is 1, what's x? Well, x has to be 3, because 3 take away 2 is 1. So notice each time x has to be 2 bigger than it was before, because you're immediately taking 2 from it. So to get the same y value, x has to be 2 bigger. So for example, to get a y value of 2, what x value do we need in here? Well, the square root of 4 is 2, so we want x minus 2 to be 4. If x minus 2 is 4, what's x? Well, x has to be 6, because 6 take away 2 is 4. Again, 2 bigger than it was before. And to get a y value of 3, the square root of 9 is 3, so we want x minus 2 to be 9, So x has to be 11. Because 11 take away 2 is 9, and then when you square root that you get 3. So notice all the x coordinates are 2 bigger than they were before for the same y values. So that means all the points are going to be 2 to the right of where they were before. So 2, 0 is going to be over here, 2 to the right of that point. 3, 1, across 3 up 1 is going to be 2 to the right of that point. 6, 2, right 6 up 2, 2 to the right of that point. 11, 3 is right at the end up here, sort of 2 to the right of that point. And this graph, this new graph, is just the original graph, but shifted 2 places to the right. It's the original graph translated 2 places to the right, which is a bit unusual. You might expect replacing x with x minus 2 for the graph to move left 2, but it actually moves right 2. It sort of does the opposite of what you'd expect. If you replace x with x minus something, the graph actually moves to the right. So that's a bit weird. What could I replace x with in the original equation for the original graph to move left 2? What would I have to replace x with in the original equation? Correct. I'd have to replace x with x plus 2. So let's do that. If I replaced x with x plus 2 instead of x minus 2, that would actually cause the graph to move to the left. So if I do a quick table of values, again keeping the y values the same as before, now to get the same y values that I had before, the x values will all need to be 2 smaller than before. And that's because I'm immediately adding 2 to them. So instead of these x values, instead of an x value of 0, I need an x value of minus 2. Instead of an x value of 1, I need an x value of minus 1, 2 smaller. Instead of an x value of 4, I need an x value of 2. And instead of an x value of 9, I need an x value of 7. I mean, we could try it out with one of those points. When x is 7, 7 plus 2 is 9, and then the square root of that is 3. So it works. So all the x coordinates are 2 smaller than before, so all the points are going to be 2 to the left of where they were before. So minus 2, 0 is going to be over here, minus 1, 1 is left 1 up 1 over here, 2, 2 is over here, 2 to the left of that point, 7, 3 is across 7 up 3, just over here, 2 to the left of that point. And this new graph is just the original graph shifted 2 places to the left. So when you replace x with x plus 2, again a bit unusual, the graph doesn't move right, it moves left 2. Right, let's move on down here. So I take the original graph, the original equation, y equals the square root of x, and this time I'm going to replace x with 2x. So I'm going to just rub that out and replace x with 2x. Notice I'm not sticking a 2 in front of the whole thing, I'm not doubling the whole expression. That would cause it to stretch vertically, we did that one already. I'm actually replacing x with something else. I'm replacing x with 2x. Because I'm replacing x with something else, that's going to cause a horizontal transformation. But again, it's difficult to predict. It might be the opposite of what you'd at first expect. So let's do a table of values. So again, I'll choose the y values to be the same. 0, 1, 2 and 3. And I'm going to think to myself, what x values do I need to get those y values that I had before? So to get a y value of 0, what x value do I need? Well, the square root of 0 is 0, so I want 2x to be 0. If 2x is 0, then x has to be 0, doesn't it? So x has to be 0, no change there. What about if I want y to be 1? What x value do I need? Well, if I want y to be 1, the square root of 1 is 1. So I need what's in here, I need 2x to be 1. Well, if 2x is 1, then x has to be a half, or 0.5. So basically half of what it was before. If I want a y value of 2, what must x be? Well, the square root of 4 is 2, so I need 2x to be 4. If 2x is 4, then x would have to be 2. Again, half of what it was before. So yeah, x needs to be half of what it was before, because you're immediately doubling it. So to get a y value of 3, what x value do I need? Well, the square root of 9 is 3, so I want 2 times x to be 9. If 2 times x is 9, then x is 4.5, so 4.5. So notice all these points, and for all these points the x-coordinate is half of what it was before. So basically all the points are going to be twice as close to the y-axis as they were originally. So 0, 0 is still going to be here. 0.51, the half 1 is across half up 1, just over here, twice as close to the y-axis. 2, 2, right 2 up 2 is just over here, twice as close to the y-axis as that point. 4.5, 3 is right 4.5 up 3, just over here. So twice as close as that point to the y-axis. So in other words, this gap here is half of what it was originally. So it's half of that gap there. The points are all twice as close to the y-axis. So if I draw the graph, it's just the original graph, but it's the original graph squashed inwards, squashed horizontally. We say it's the original graph squashed by a scale factor of 2, which just means that all the points are twice as close to the y-axis. All the x-coordinates are half of what they were before. Again, that's a bit unusual. You might expect that replacing x with 2x would cause it all the distances to double. You might expect it to stretch by a scale factor of 2, but it actually causes it to squash by a scale factor of 2. Now, what would I need to replace x with to stretch it by a scale factor of 2 for the distances to double, do you think? What would I need to replace x with? Correct! You need to replace x with x divided by 2, or half x. So let's do that. So I'm going to replace x with half x. That actually causes it to stretch by a scale factor of 2. Because to get the same y values that you had originally, the x values now need to be double what they were before, because you're immediately halving them. So you need, instead of these x values, you need x values twice as big. So you need an x value of 0 doubled is 0, 1 doubled is 2, 4 doubled is 8, and 9 doubled is 18. These are the x values you'd need to get the same y values as before. We could try it out. If you put 18 in there, half of 18 is 9, and then the square root of that is 3. So it works. So on the grid, these points would actually be twice as far away from the y-axis because their x-coordinates are all double. So 0, 0 is still here. 2, 1 is right 2 up 1, just over here. 8, 2, right 8 up 2, just over here. And 18, 3 is right 18 up 3, so that's way off the grid. So this graph is basically, it's the original graph stretched. So all the points are twice as far from the y-axis as they were originally. So it's been stretched by a scale factor of 2. Again, that's a bit unusual. Replacing x with half x, you might expect the distances to halve, but they all double and the graph becomes stretched. So with horizontal transformations, what actually happens is the opposite of what you expect, usually. Right, let's go down here. So I'm going to start with the y equals the square root of x. And this time I'm going to replace x with minus x. So let's see what happens here. So I'm going to replace x with minus x. Notice I'm not sticking a minus sign in front of the whole thing. That would cause it to flip vertically. If you do something with the whole expression, that causes a vertical change. I'm actually replacing x with minus x. Because I'm replacing x with something, it's going to be a horizontal change. So I wonder what's going to happen. Let's do a table of values. And again, to understand the horizontal change, I'm going to keep the y values the same. And I'm going to think to myself, what x values do I need to get those y values? Well, to get a y value of 0, well, the square root of 0 is 0, so I need minus x to be 0. Well, if minus x is 0, then x is 0. So no change there. If I want y to be 1, the square root of 1 is 1. So I need minus x to be 1. Well, if minus x is 1, then x is minus 1. To get a y value of 2, the square root of 4 is 2. So I need minus x to be 4. Well, if minus x is 4, then x has to be minus 4. So the x values are just, each x value is just the negative of what it was before. And to get a y value of 3, the square root of 9 is 3. So minus x has to be 9. In other words, x has to be minus 9. Because when you put minus 9 into there, minus 9 is 9, and then the square root of that is 3. So notice for each point the x value is just the negative of what it was before. So all the points are going to be over here with negative x coordinates. 0, 0, just over here. Minus 1, 1 is left 1 up 1, just over here, just a reflection of that point in the y-axis. Minus 4, 2 is left 4 up 2, just maybe over here somewhere, a reflection of that point in the y-axis. Minus 9, 3 is going to be left 9 up 3, so maybe way over here somewhere, a reflection of that point. And the graph is just going to be sort of like, it's the original graph, but it's the original graph reflected in the y-axis. It's a horizontal reflection. So if you replace x with something else, x minus 2, 2x minus x, it causes the graph to change horizontally. And with horizontal transformations, what happens is usually the opposite of what you'd expect. So if you replace x with x minus 2, the graph doesn't go left 2, it actually goes right 2. If you replace x with 2x, it doesn't stretch by a factor of 2, it actually squashes by a factor of 2. So what I'm going to do now is I'm going to do a mixture of horizontal and vertical transformations for a different graph. Right, I'm going to do some transformations now for the graph y equals x squared. So I'll do a table of values for this graph so you can see what it looks like. Now when I do the transformations, I'm going to go much quicker this time. I'm not going to do a table of values for each transformation, I'm just going to sketch it straight away. But let's do a table of values for the original graph for y equals x squared so you get a good idea of what it looks like. So I'm going to choose these x values, 0, 1, 2, minus 1 and minus 2. Let's find the y values that go with them. So when x is 0, 0 squared, 0 times 0 is 0. When x is 1, 1 squared, 1 times 1 is just 1. When x is 2, 2 squared is 4. When x is minus 1, minus 1 squared, minus 1 times minus 1 is 1. A negative times a negative is always positive. When you put minus 2 in, minus 2 squared, minus 2 times minus 2 is 4. Again, a negative times a negative is always positive. So let's plot these points on the grid. So 0, 0 is here, 1, 1 is here, 2, 4, right 2 up 4, minus 1, 1 is left 1 up 1, minus 2, 4, left 2 up 4, just over here. So the graph looks like this. It's symmetrical, and all the y values are positive, because when you square a number you always get a positive answer. So what I'm going to do now is I'm going to make 6 copies of the same graph. Right, so I've drawn 6 copies of y equals x squared. So let's do some transformations. So let's take the original graph, sorry, the original equation, y equals x squared, and stick a plus 1 on the end. So let's do that plus 1 on the end. So what effect is that going to have on the position of the graph? Well, if you remember from the last example, if you add a number onto the end of the expression, it sort of moves the graph up. So the whole graph is sort of going to move up 1, basically. It's going to translate 1 place up. So let's say this point's going to move up 1, 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 this point's going to move up 1. So I'm just imagining moving some points up. I mean, there's no scale, so I've just got to imagine doing it. But the new graph is going to look something like this. So the whole graph has been translated up 1. What would happen if I, instead of adding 1 onto the end, if I drew the graph of y equals x squared, take away 1? So what's that one going to look like? That's right, it's going to move 1 place down. It's the original graph translated 1 place down. So this point here is going to move down 1, this point here is going to move down 1, this point here is going to move down 1, this point here is going to move down 1, this point here is going to move down 1. So the graph is going to be the original graph, but translated down 1 this time. Right, let's take the original equation, y equals x squared, and let's multiply the expression on the right hand side by 3. So let's do y equals 3x squared. Y equals 3x squared. Sorry, messed that up a bit. Y equals 3x squared, so multiplying the whole expression by 3. So what effect is that going to have on the graph? Well, again, I'm doing something to the whole expression. I'm multiplying the whole thing by 3, so it's going to be a vertical transformation. And if you remember from the first example we did, when you multiply the whole expression by a number, the graph either stretches if it's a number bigger than 1, or it squashes if it's a fraction. So, so this is going to cause the graph to stretch sort of by a factor of 3. So all the y coordinates will be 3 times bigger than they were originally. And all the points are going to be 3 times higher than they were, sort of 3 times further from the x-axis. So this point is going to move way up here somewhere, 3 times further from the x-axis. This point's going to move up to here maybe. This point perhaps up to there. This point up to there maybe. This point's on the x-axis, so it's going to stay where it is. So the whole graph is sort of going to stretch upwards, so that all the points are 3 times higher, 3 times further from the x-axis than they were originally. So something like that. A vertical stretch by a scale factor of 3, you could say. And what about, instead of multiplying the expression by 3, I divided the expression by 3, or multiplied by a third, same thing. So what if I did y equals x squared times a third? What effect is that going to have? Correct! It's going to squash down by a factor of 3. So this point is going to be 3 times closer to the y-axis over here. Sorry, 3 times closer to the x-axis. This point here is going to be 3 times closer to the x-axis, maybe over there. This point's going to go over there, this point over there. This point's on the x-axis, so it's going to stay there. So it's going to squash right down. So all the points are 3 times closer to the x-axis. So it's a vertical squash by a scale factor of 3, you could say. Now what about if I took the original equation, y equals x squared, and I just stuck a minus sign in front of the expression on the right-hand side. So y equals minus x squared. So what effect is that going to have? Well, again, I'm doing something to the whole expression on this side. I'm sticking a minus sign in front of the whole thing. So again, it's going to cause a vertical transformation. And if you remember from earlier, just sticking a minus sign in front of the expression reflects the graph in the x-axis. So all the y-coordinates change sign. So these points up here are sort of going to get reflected down here. So this point's going to get reflected down. This point's going to get reflected down. If there were any points down here, they would get reflected up, but there aren't any on this graph. And this point is going to sort of stay where it is because it's already on the x-axis. So this new graph is a reflection of the original graph in the x-axis. Right, so all these transformations so far have been vertical transformations, and that's because I've done something to the whole expression. To get horizontal transformations, if you remember, you have to actually replace the x with something else. So let's do some horizontal transformations over here. So instead of drawing y equals x squared, let's replace x with x plus 1. So let's replace x with x plus 1. So what effect is that going to have on the graph? Well, I'm replacing x with something, so it is going to be a horizontal transformation. And if you remember from the last example, if you replace x with x plus something, the graph doesn't move to the right, it moves to the left. So the graph is actually going to move to the left one place. With horizontal transformations, it's usually the opposite of what you'd expect. So let's move some points one place to the left. This point's going to go one to the left, this point's going to go one to the left, this point's going to go one to the left, this point's going to go one to the left, this point's going to go one to the left. Again, there's no scale, so I'm just having to imagine moving the points. If you did this on square paper, you could actually move some points using the squares. And when you've done enough points, you could then join them up. So it would look something like that. And what if I were to replace x with x minus 1 instead of x plus 1? So if I were to replace x with x minus 1, what effect would that have on the graph? That's right, it would move one place to the right, not left. So this point would move one place to the right, this point would move one place to the right, this point would move one place to the right, this point would move one place to the right, this point would move one place to the right. So it would be a translation of the original graph, one place to the right. So again, the opposite of what you might expect. Right, let's take the original equation of the graph, y equals x squared, and let's replace x this time with 3x. So let's draw y equals 3x all squared. So what effect is that going to have on the position of the graph? Well, if you remember from earlier, if you replace x with something times x, it's either going to stretch it horizontally or squash it horizontally. If you replace x with 3x, it's not going to stretch it by a scale factor of 3, it's going to actually squash it by a scale factor of 3. Again, the opposite of what you might expect. So all the points are going to end up 3 times closer to the y-axis. So this point is going to move 3 times closer, this point is going to move 3 times closer. This point may be over here, this point may be going to move over here. This point's on the y-axis, so it stays where it is. So the whole graph gets squashed, so it's 3 times closer to the y-axis. Something like that. And what about if instead of replacing x with 3x, I replaced x with a third x, let's say. Replaced x with a third x. Do that in green. So what effect would that have on the graph? Again, it's the opposite of what you might expect if you haven't seen this before. It doesn't squash it by a factor of 3, it stretches it horizontally by a factor of 3. So all the points end up 3 times further from the y-axis. So this point maybe moves over here, this point over here perhaps, this point over here maybe, this point over here perhaps. This point's on the y-axis, so it stays where it is. So the graph stretches out horizontally, so that all the points are 3 times further from the y-axis. So one more. So let's take the original graph, the original equation, y equals x squared, and let's replace x with minus x. So I'm going to replace x with minus x. So what effect is that going to have on the graph? Well, we saw that when we stuck a minus sign in front of the whole thing, that reflected it vertically in the x-axis. If you replace x with minus x, it's going to do a horizontal transformation, and it's going to reflect it in the y-axis. So we need to reflect this graph in the y-axis. So this side is going to get reflected across over to here, and this side is going to get reflected over to there. So this particular graph doesn't change when you reflect it in the y-axis, because the y-axis is a line of symmetry for this graph. So when you reflect it in the y-axis, it just flips sort of on top of itself. And if you look at the equation, you might be able to see why. Minus x squared, or minus x times minus x, is just x squared. So the negatives sort of cancel each other out. So this equation is exactly the same as y equals x squared. So because it's the same equation as y equals x squared, the graph is of course exactly the same. But generally, if you replace x with minus x, it causes the graph to reflect in the y-axis, reflect horizontally. So notice that for the horizontal transformations, I've had to replace x with something else. That's how you get a horizontal transformation. For a vertical transformation, you just do something to the whole expression. Like add 1, multiply by 3, stick a minus sign in front of the whole thing. And for horizontal transformations, you've just got to be careful, because usually what happens is the opposite of what you might expect. So if you replace x with x plus 1, it doesn't move to the right one, it moves to the left one. Or if you replace x with 3x, it doesn't stretch by a factor of 3, it actually squashes by a factor of 3. So that's it.